Hey there. Lecture 12, Part B. We're going to start with the probability tree and we should finish this up. I'm going to skip independence on 8.3. Anyways, let's go. So, basically, a probability tree is a nice way to think about probabilities. It helps lay out the different possibilities when you have sequential events, when you have one event and then another event and then another event, and each one depending on the previous, especially. So, let's say that you've got two balls that are drawn in succession, one right after, without replacement, from a box containing three blue balls and two white balls. So what is the probability of drawing a white ball on the second draw? Okay, I'm gonna turn my video off here. So what we can say is that the sample space is equal to, well, we're drawing two balls, blue and white, so we can have white white, white blue, blue white, and blue blue. That's the only possibilities we can have. But also, let's think about it. We notice that the probabilities change. They're not going to be the same because once you pick a ball without replacement, that probability changes. So this tells you this. Maybe using a probability tree would be a good idea. So when we do this, we start and we just kind of make a branch, and we say, okay, we put white here, blue here, and then we look. What's the probability of drawing a white ball? There's five total balls, right? In the first draw, there's five total. So two of them are white. So 2/5 and 3/5 for blue. And then now we can draw a white or a blue. And from here we can draw a white or a blue. But we no longer have five balls in the box. We now have, if we're up on the top, we have one white ball and four balls total. So we've got one white ball, so 1/4 and 3/4. For on the bottom, we have two blue balls and two white balls. So 2/4 and 2/4. Now, let's multiply these out. So if we're looking at it, we say, well, a white ball and a white ball. So two white balls. We multiply these together, and that'll give us 2/20, right? Which is equal to 1/10. 6/20, 6/20, which is equal to 3/10. Again, 6/20, so 3/10 and 3/10. 3/10. And I'm going to do a quick double check. I've got 1 plus 3 plus 3 plus 3 is 10/10. So the total, the sum here, is equal to 1, and that's what I would expect. So the probability of doing a white on the first is 2/5, and on the second, and then on the second row we have this. And then we have the intersection. So basically, this is the intersection of white and white. This is the probability of white and white. This is a conditional probability given that we rolled white already. So these in here are conditional probabilities. So the probability of white given white is equal to 1/4. The probability of white intersect white is equal to 1/10. Probability of white given blue, so that would be the second one, is 2/4 or 1/2. So it's 1/2. And the probability of the first one being blue intersect white And now here's where it gets a little bit tricky sometimes. But because it depends on how you view it. So you could view these two being as the same or different events. Now we're viewing them as being different. So that means the order matters. A lot of times it won't. Okay? But we did calculate the intersections, and we calculated this as 3/10. And the other ones are indicated here. They're basically the same calculations that we just did. I don't think there's any point to belabor that. You can always revisit it. We check our calculations, and what I mean by checking the calculations is if we look at the probability coming off of this, 1/4 plus 3/4 is 1. So we're looking at the branches, so we've got 2/5 and 3/5 is 1. The ending ones are 1/5, 1/10, 3/10, 3/10, 3/10, which is 1. So it's a way of double checking that your numbers are working out, and that's something you kind of get a hang of. And recall, we are asked, what is the probability of white on the second draw? Is that what we were asked? Let's double check. What were we asked? What is the probability of drawing a white ball on the second draw? So the probability of drawing a white ball is equal to the probability of drawing white and blue-white, right? So the probability of white on second is equal to 1/10 plus 3/10, which is equal to 4/10. And that's what we're indicating. That's what we're indicating here. Okay. How do you go about drawing a probability tree? I think you kind of got the hang of it by what I demonstrated, but let's just be a little bit more explicit about how we're saying this. So you consider all the possible outcomes. So you draw a tree diagram and you kind of lay it out, and then you label each node, and then you assign a probability to each tree branch. And when I do it, I pick one to go first. Doesn't matter white or blue, but then I try and maintain that order as I'm going through it. It just kind of helps. So I end up with, and it matches up very well with this. So I end up with white, blue, white, blue. So I kind of write it so that these two things match up, and that comes with a little bit of experience. Then we assign probabilities to each branch, starting at the root, if possible, and then going from there. These are conditional probabilities, and then we calculate the intersectional probabilities via multiplication, 2/5 times 1/4, 2/5 times 3/4. And then we answer any questions that we have related to the experiment. So this is basically the exact same experiment, only we're going to rerun the experiment, only now we replace any ball selected. So instead of what we had previously, and I'm going to leave it out so that you can see it, which is 2/5, 3/5, which is exactly the same as what it was. But then we had 1/4 and 3/4. Now we're still going to have the exact same thing that we did in the first step. We're going to have 2/5, 3/5, and 2/5, 3/5. And that's going to change what our calculations are. So then we have, coming out, we've got 4 25ths for white and 6 25ths for blue. So these are our intersectional probabilities coming out, which is just multiplying this times this to get this top one. Okay? Again, 4 plus 6 is 10, plus 15 is 25. So again, this should total 1. It's a very different result. Because we were doing a replacement, it kind of leads to what we call independent events, and this is kind of what I'm going to gloss over. I'm actually going to skip it in this lecture, so let's just keep on moving. Okay? I may just run over this example This example asks about independence. Don't worry about that part of it. Let's just consider the rest of it. Let's make sure that we're able to draw the tree and label everything appropriately. So let's do this example for labeling and the tree, okay? So we have, let A be the event that all of the family's children are the same gender, and let B be the event that the family has at most one boy. So A. So we have a family. The probability of having a boy and a girl is exactly the same. In one set, they have 2 children. And in the other, they have 3 children. So I'm going to do this, and I'm going to go boy, girl. Okay. Boy, girl. I'm going to make sure, I'm going to do it the exact way I have it in my example, which is girl, boy. So let me put a G up above. That way it'll look the same as what I end up with on my notes. So this will be a G, this will be a B. Probabilities are even, 0.5. So I'm going to use 1/2, 1/2. Girl, boy. Girl, boy. And I'm going to do one more off of here. Girl, boy. Girl, boy. Girl, boy. Girl, boy. Now what you'll see is this is G, 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 B, B, G, B, B. So we can determine our sample space. So for S2, our sample space for 2 generations, 2 children, is GG, GB, BG, and BB. And we can continue that through and say GGG, GGB, GBG. So I'm gonna do the next one. So the sample space for the 3 children is GGG, GGB, GB, G. Okay, that's this. Now we're going to go down to our lower branch. Oops, I'm missing one, aren't I? Ah, yeah. GBB. Now, let's recall. How do we know how many events are there supposed to be in here? Well, this is kind of a review. So we have 3 separate things. So we've got 1, 2, 3 operations. In our first operation, it's 50-50, but so it's 2 possibilities. So it's 2. In our second operation, there's 2 possibilities, 2 times 2. In our third, there's 2 possibilities, 2 times 2 times 2. So there's 8. 8 possible items that should be in our sample space. So now we'll have BGG, BGB, BBG, and BBB. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And we drew the tree already. So, in fact, I drew the tree before I pulled out the sample space, but you could do that one either way. Sometimes it's actually easier to draw the tree and pull the sample space from the tree, but it's not required. Now, let's calculate our probabilities. Remember, it's 50% every single time. That doesn't change. So it's always 1/2. Right? 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. Now, I can calculate coming into this one. So I've got a GG, a GB, a G. So now there's 4 of these. 1/2 times 1/2 is 1/4. So these are each going to be 1/4. Yes? Now each one of these is going to be 1/4 times 1/2, so each one of these is going to be 1/8. They're all equally likely, and there's 8 possibilities, so it's 1/8. all the way down. Good. There. That's our probability tree. Now, I drew it pretty fast. It's basically the exact same thing as what we have here. Okay. Now, the questions that we were asked is, A is the event that all of the family's children are the same gender. So what is the probability of A? So the probability of A that they're, and this is for 2, so sub 2. So when we're talking about 2, the probability that they're all the same gender, it should be 1/4 plus 1/4, 1/4 plus 1/4 equals 1/2. You could also do that by looking at our sample space and say there's 1, 2 divided by 4, which is 1/2. Okay, so what is it when we're talking about for 3 children? The probability of event A when we have 3 children. So when we're doing that, we have 1/8 and 1/8. So there's only the 2 possibilities. So it's 1/8 plus 1/8. And that is 1/4. You could also view it as looking at our sample space and picking out 1, 2, 2 divided by 8. So there's multiple ways to get to this answer, but the answer is still going to be 1/4 and 1/2. 1/4 and 1/2. The other thing that we're measuring is let B be the event that the family has at most 1 boy. So at most 1 boy. So at most 1 boy, and at most 1 boy, when we're talking about for the first one, at most 1 boy, there's 3/4. We're just taking out one of them. So it's 3/4. So the probability given 2 of B is equal to 3/4. So that would be 1/4, 1/4, 1/4, not include that. So there's multiple ways to get to some of these answers sometimes, okay? And then given 3, the probability that they have at most 1 boy, at most 1 boy. So we don't want this. We don't want this branch. That has 2. In fact, this has anything coming down here has 2. So take out this branch. So we've got 1/8, which is this one. And then we have 1/8 plus 1/8 plus 1/8. So and that equals 1/2. Okay. Could we also calculate that using our sample space? Of course we could. Let's calculate that using our sample space. In that case, we would have 1, 2, 3, 4, 4 divided by 8, which is 1/2. So we're going to get that same result regardless of how we calculate that. I'm not going to do the other part of this because it talks about independence, so we're going to skip that part of it. Thank you very much. That covers conditional probability. And that will be the extent of what is on exam number 2. Thank you.